for people to watch it later also. So, vamos a iniciar entonces la plática que tenemos con la doctora Uma, así es, su nombre es S.K, y les vamos a hablar, ella nos va a hablar sobre las tablas astronómicas. Les voy a dar una pequeña introducción de lo que ella va a hablar. Sobre la necesidad e importancia de las tablas astronómicas a lo largo de los siglos para calcular posiciones planetarias y algunos fenómenos astronómicos. Es bien sabido que en el mundo occidental son famosas algunas tablas astronómicas, las compuestas por Ptolomeo, Copérnico, de la Hire, Brown, Leverrier, Simon, Newcomb, como también las tablas persas. De manera similar, en la India se compilaron tablas astronómicas en sánscrito y más tarde en otros idiomas indios. Estas tablas astronómicas indias se calculan utilizando procedimientos matemáticos para las longitudes medias y verdaderas, la ecuación del centro, la ecuación de conjunción, la segunda ecuación, diámetros angulares. Estos se basan en algunos textos sánscritos canónicos sobre astronomía matemática como Aryabhatiya y Suryasiddhanta. También se muestran folios de muestra de algunas de estas tablas y también se proporcionan algunos ejemplos ilustrativos para el beneficio de un estudio más profundo del tema de parte de los estudiantes interesados. Se agrega una bibliografía exhaustiva al final de la presentación. Quiero decir que la doctora Uma es doctora en astronomía, tiene un doctorado en astronomía y está hablando desde la India y para ellos pues está amaneciendo ahorita, son las 7 de la mañana, 7:30 y entonces nos va a compartir este conocimiento que a nosotros para esta charla es bien significativa porque no solamente es conocimientos astronómicos, sino también una charla cultural de amplio espectro. Así que le damos la bienvenida a todos ustedes para acompañarnos. Esperamos que se unan más personas a lo largo de esta charla y luego también tendremos este documento grabado para su conveniencia. Voy ahora a presentar a la doctora y ya para que inicie su charla. Muchas gracias. Dr. Uma, thank you for being with us tonight. Here in Guatemala is the evening, so you can please go ahead and share your presentation for us to see it, and please go and start.
Thank you very much, Professor. Thank you for the nice introduction and also for inviting me for giving a talk and sharing some of the information which I know regarding Indian astronomical tables. Thank you, sir. I'll share the PPT. Yeah.
Okay.
Will you able to see the PPT, sir?
Yes, we are looking at the PPC.
Okay, sir. Thank you.
The
so
PPT.
Much.
Yes. Yes. Can you play it in presentation mode?
Yes, I'm just checking for that.
All right.
Is that okay, sir? Now?
We are looking not in presentation mode.
Okay, just a minute.
Now we are okay.
Okay, fine.
Perfect. Thank you. So we are ready. Thank you again. Thank you one more time for your time, dear Dr. Uma.
Good evening and good morning, one and all who have joined for the presentation. I'm Dr. Uma. I'm speaking today on Indian astronomical tables. we shall take the history of astronomical tables in Europe and Arabic world. Astronomical tables basically designed to facilitate the calculation of planetary positions, lunar phases, eclipses, and calendrical information. They often included explanations of astronomical instruments also. These tables were necessary in the European and Arabic worlds to prepare planetary charts and eclipses. Ever since the time of Babylonians, theoretical models have been developed for predicting the time of occurrence and location of celestial phenomena. Unfortunately, without calculators or computers, performing even the simplest calculations with these models was cumbersome and time-consuming. Astronomical tables were constructed to simplify the procedure. In the Almagest, Ptolemy showed how to construct tables that made this procedure much more tractable. The works of Ptolemy
we stopped. Cannot hear you. Hello, doctor.
Can you hear me, sir, now?
Yes, now we can see. We can hear you now.
As Muslim scientists became increasingly familiar with the Hellenistic, Hindu, and Persian astronomical lore, more sophisticated methods were developed to deal with these secular and religious needs. At a later stage, based on the revised values, new tables were computed in various, according to various meridians and radiuses given for the date of the Hijrah in 1622. The tables were collected into handbooks known as jizis, along with the tables for mean motions, radiuses, and correction factors. These included accurate calendric, prayer, and Fibla tables. They also often included various trigonometric tables indispensable for solving problems of spherical astronomy as well as star catalogs. The introduction to a JIS would usually discuss the underlying model and specific parameter values used to construct the tables along with canons for their use. The Alfonso tables became the most influential handbook of the practical astronomy in Europe. It was the basis for almost every almanac in ephemeris till 1551 CE. Erasmus Reinhold, the Tabulae Proteniaceae was the first practical set of planetary tables based on Nicolaus Copernicus' Hellenistic theory. Reinhold cast his tables in essentially the same format as alpha sign tables. Alpha sign tables, also spelled as Alphonsine tables, the first set of astronomical tables prepared in Christian Europe. They enabled calculation of eclipses and the positions of planets for any given time based on the Ptolemaic theory. The tables were not widely known, however, until a Latin version was prepared in Paris in the 1320 CE. Copies rapidly spread throughout Europe, and for more than 2 centuries, they were the best astronomical tables available. First printed in 1483 CE, the Alphonsine tables were an important source of information for the young Nicolaus Copernicus before his own work superseded them in 1550s. When we come to the astronomical tables in Europe, early in the 19th century, the methods of predicting the motion of planets were somewhat scattered, having been developed over decades by many different researchers. In 1847, Leverrier began by reevaluating to the 7th order techniques of calculating the planetary perturbations known as the perturbing function. This derivation, which resulted in 469 mathematical terms, was completed by 1849. Leverrier published in the de Paris tables of the motions of all of the known planets, releasing them as he completed them starting in 1858. The tables formed the fundamental ephemeris of the astronomical almanac, the Bureau des Longitudes, until about 1912. About that time, Leverrier's work on the outer planets was revised and expanded by Gaillot. Philippe de la Heyrie was a French mathematician and an observational astronomer who worked in the Observatory of Paris. Over the decades, he made numerous observations and calculated tables of the movements of the sun, moon, and planets. He published two main sets of astronomical tables, and the later one was reprinted in 1727 and translated into French in 1735 with revisions. Now we shall come to the Indian astronomical table. In India, in Indian society, for observances of religious festivals and also for civil purposes, the calendrical almanac called Panchanga is a necessity. Compilation and use of annual Panchanga. It is called as Panchanga in Sanskrit, which is the annual almanac. It is a socio-religious necessity in Hindu society. In the Indian tradition, the astronomical almanacs are published annually according to different schools of astronomies. The different schools of astronomy are called as Pakshas in Sanskrit, and they are named as Saura, Arya, Brahma, and Ganesha Pakshas. The annual, I will give some more information about these Pakshas in the later slides. The annual almanacs are computed using different sets of astronomical tables like Makaranda Sarni, Ganakananda, Pratibhagi, Mahadevi, Titi Chintamani, and Vakya, etc. All these names are in Sanskrit. The Indian astronomical tables are called differently as Sarini, Padakam, Kostaka, and Vakya. These are the different Sanskrit terminologies used to tell the astronomical tables. Since the direct application of the major texts, Siddhantic text, is cumbersome and tedious for day-to-day positions of heavenly bodies, the Panchanga or the almanacs are compiled annually based on the tables of different Siddhanta Pakshas, I mean different schools of astronomy. Just connect. These different schools of astronomy would list the sequence of the Panchangas based on these different schools of astronomy would list the sequence of all the days in the year along with the specific times during each day, marking the transitions of the other time units and occurrence prescribed religious rites and festivals along with the particular auspicious or inauspicious celestial events such as eclipses. The flexible and innovative construction of astronomical tables called Sarini is the increased computational convenience and efficiency for their users, as well as affording the outlets for the creative ingenuity of their authors. But the close relation between these astronomical types does not mean that every astronomical table is merely a record of mechanically repeated applications of some algorithm prescribed by a handbook called Karana. Karana is the Sanskrit name used to represent the handbook. A table compiler might combine, simplify, or otherwise modify algorithms from various sources to produce his tabulated values. The interpolation techniques were constantly invoked to ease the labor of filling in indeterminate values with a table once certain key entries had been computed by more complicated method. Let us see what is meant by Panchanga. By the word itself, Panchanga is fivefold. Panchanga is the traditional Hindu almanac. In a traditional Hindu household, the annual Panchanga is indispensable. A Hindu uses Panchanga for all his religious observances and also for ascertaining the dates of important religious festivals. As the word itself indicates, Panchanga consists of 5 parts. In Sanskrit, Pancha means 5, Anga means parts. So the 5 parts of the Panchanga are Tithi, Nakshatra, Vara, Yoga and Karana. These are all Sanskrit names. So let us find out what are these Tithi, Nakshatra, etc. The 5 parts of Panchanga. So I'll give some information about these things in later states. Tithi means lunar mansion. Nakshatra is Tithi is the lunar day. Nakshatra is lunar mansion or asterism. Vara is the weekday. And Yoga is the combination of the positions of sun and moon. And Karana is half of the Tithi, half of the lunar day. Name of this ephemeral type refers to the 5 chief time units whose passage the calendar tracks. All of these can approximated by mean or average versions based on assumptions of uniform angular motion for the sun, moon and the lunar node. The lunar node is called as Rahu in Sanskrit. But the construction of calendar generally requires taking into account their derivation from uniform motion so that, for example, sunrise or full moon will correspond more or less to the observed moment of the astronomical phenomenon in question and not just to the passage of an average time unit. In a Panchanga or the Hindu ritual calendar, equal on average to 1/13 of a synodic month. It is the measure of the phases of the moon. Tithi in Panchanga or Hindu calendar is the 1/30th of a synodic month. It is the measure of phases of moon. We can note here in modern astronomy, we have some recognized some 7 to 8 phases of moon, but in Indian system, they have recognized 30 phases of moon and each phase is named as a Tithi. We have names for different phases. I will give the list of the names in the next slide. Worship ceremonies are typically celebrated with reference to a given Tithi of a given month rather than to a civil day. The astronomical definition of a Tithi or the lunar day is the time period during which the elongation of angular separation between the longitudes of the sun and the moon increases exactly by 12 degrees. Since the irregularities of the sun's and moon's motion causes variations in their apparent speed, the length of a true Tithi is constantly changing, generally falling a little short of but sometimes exceeding the length of a mean civil day. A professional almanac or Panchanga maker is required to determine at exactly which times in which successive days a given Tithi starts and ends, and which Tithi falls on entirely within a single civil day, and which extended beyond a given civil day on both the sides. So if it falls entirely within a single day, we just call it as omitted Tithi, and that is Kshaya. And if it exceeds a civil day, we call it as additional Tithi. The Vara or weekday indicates a given date's position in the familiar regular 7-day cycle. It is never deliberately interrupted or intercalated. Now here we have the phases of moon. See the picture A here. Starting from A, the phases of moon are shown here. The new moon to the next new moon. The shape and size of the moon changes from day to day. On an Amavasya day, see the new moon day in Sanskrit is called as Amavasya. The moon is invisible here in A, position A. On the next day, a very thin crescent moon, that is the position B, is visible in the sky. If the sky is clear, soon after the sunset in the western horizon. On the succeeding days, the Shukla Paksha is called the bright fortnight, starting from the first after the Amavasya, from the first day to the next full moon day. So we call that 15 days of fortnight as Shukla Paksha. On the succeeding days of the first fortnight, the brighter or visible part of the moon keeps on growing until it is half, that is position C, on the 7th or 8th day after the new moon. Also each day, the moon keeps moving up in the sky at sunset, since it moves farther from the sun at the rate of about 12 degrees per day. When the phase of the moon is half, it will be midway in the sky between the eastern and the western horizons. Then each succeeding day, the brighter part of the moon grows more than half when it is said to be gibbous, that is the position D. At the end of the first brighter fortnight, that is the Shukla Paksha, the moon will be fully visible. It is the position E, which is nothing but the full moon day. And after that, the Krishna Paksha starts, that is the dark half of the month, that is the second fortnight of the month commences. Now I have given the list of tithis here. So the tithis are named in Sanskrit. I'll just give you this. So they are called as Prathama, Dvitiya, Tritiya, etc. Prathama means first day after the new moon. Dvitiya is the second day. Tritiya is the third day. Like that it goes on. So we have 15 tithis in the first fortnight, and the 15th tithi is called as Purnima. That is the full moon day. After that, again we count the tithis as Prathama, Dvitiya, Tritiya, etc. Again, that means it is the first day after the new moon, second day after the new moon, etc. And when it comes to the 15th day after the new moon, and that after the full moon, the 15th day, that means the 30th day of the lunar month will be the Amavasya. The full moon day is called Purnima. New moon day is called as Amavasya in Sanskrit. Other names of the tithis will be repeated. And the mathematical expression for finding the tithi is given as longitude of the moon minus longitude of the sun divided by 12 degrees, when both the longitudes are expressed in degrees. See, to calculate tithis, so we use this formula. The quotient part indicates the number of tithis completed during that lunar month, and hence the quotient plus 1 gives the currently running tithi. If the tithi is less than 15, then it is the Shukla Paksha, that is the first brighter fortnight. If the tithi is greater than 15, then we subtract 15 from that number, and the remainder gives the running tithi in the Krishna Paksha, which is the darker fortnight, that is the second half of the lunar month. If the tithi is 15, then it is Purnima, full moon day. And if the tithi number comes to 30, then it is the new moon day, that is Amavasya in Sanskrit. If the longitude of the moon is less than that of the sun, then we add 360 degrees to avoid the negative sign, and then divide it by 12 to get the number of the tithi number for the given day. So this is the mathematics part of the calculation of tithi. And again we come to this. So we can see from this figure. So when we start from the position A, it is the new moon day. The moon is not visible, and after that we have after full moon, from the position of E, we can see that the phases of moon, it goes on diminishing and in the reverse order. See, when we start from the new moon to full moon, the brighter part we can go on seeing. And when we start from full moon to the new moon, so the moon phases goes on diminishing in the reverse order. From the full moon up to the 7th or 8th day, up to the 7th or 8th day, more than half the moon is bright when it is said to be gibbous. Then the Saptami or Ashtami, that is almost this part, position C, we call it as Saptami or Ashtami in Sanskrit, or that means 7th or 8th Tithi, 7th or 8th lunar day, the moon will be half. The bright portion of the moon goes on decreasing till it is crescent. This is the H. And again, and before the new moon day, at the end of the Krishna Paksha, that is the dark half, the dark fortnight of the month, the moon is totally invisible. The new moon day, that is I. The lunar month, as it is told already, it is divided into 30 parts. Each part is called as Tithi. That means the lunar month is divided into 30 phases, and it is also called as lunar day. And in Sanskrit, they are called as Tithis. In modern astronomy, only 8 phases are recognized, and we have given names for all 30 phases. So the bright half has 15 tithis, as I mentioned already, and the dark half also has 15 tithis. The duration of different tithis are not equal because it depends on the motion of the sun and moon in a fortnight, which is called as a paksha. Starting from the new moon or full moon, there are 15 tithis. So for giving you more clarity, an example has been calculated how exactly the lunar phases or lunar day or a tithi is computed. So I have the longitudes of the sun and moon for a given date. So the sun longitude is denoted here as S, and moon's longitude is denoted by capital letter M. So we have sun's longitude is 11 signs, 6 degrees, 46 minutes and 42 seconds. Moon's longitude for that day is 4 signs, 27 degrees, 44 minutes and 45 seconds. And according to the formula, so we have the Tithi day is given by M minus S plus the 360 degrees, because moon position is greater than the sun. To avoid the negative sign, we have added 360 degrees. And when it is divided by 12, we have got the quotient as 14.24728, etc. So that means what? We concentrate on the integer part of this. So 14 tithis or lunar phases are completed, and plus 1 if you make, 15 tithi is running. 15 tithi means it is the full moon day of the bright fortnight. So this is how mathematically we calculate tithis. And when we come to the next part, second part of the Panchanga or Almanac, so Nakshatra or lunar mansion or asterism, it is a purely lunar time unit indicating time required for moon to traverse an arc of 13 degrees 20 minutes in longitude or 1/27th of the ecliptic. In Arabic astronomy, Nakshatra is called Manzil. The reason why there are 27 nakshatras is that the moon takes 27.32 days to go around the earth once. Therefore, approximately 1 nakshatra or 1 lunar mansion is taken as 1 day. Its true value depends on the varying speed of the moon and requires more complicated calculations than the uniform interval of the mean nakshatra. Moon is called the lover of the nakshatra Rohini, which is nothing but the Aldebaran. That is because astronomically, the number of lunar occultations of star Aldebaran in a cycle is the largest. So we have the list of nakshatras. All these names are in Sanskrit. I will just read out 1 or 2, Ashwini, Bharani, Kritika, etc. And we have the 27th nakshatra, which is called as Revati. So these are the names of 27 nakshatras given in Sanskrit. Now mathematically, to calculate what is the nakshatra running for a given date, we use the formula moon's longitude divided by 13 degrees 20 minutes. So for a given day, we have taken the date March 27, 2008 at 5:30 a.m. we have taken the longitudes of the moon as 4 signs, 27 degrees, 44 minutes, 45 seconds. When it is divided by 13 degrees, 20 minutes, it is put in decimal 13.33, etc. So we get the number 11.081. So when we consider the integer part, it shows that 11 nakshatras are completed and we are running with 12th nakshatra, and the name of the 12th nakshatra or the asterism in the list was Uttara Palguni. This Uttara Palguni in Sanskrit is the ongoing nakshatra at the given time, and it is actually the Beta Leonicus or Denebola. Uttara Palguni is nothing but Denebola or Beta Leonicus. So this is how we compute nakshatra. And the third part of the almanac or Indian Panchanga is called as yoga. The yoga is the interval during which the sum of the suns and moons longitudes increases by 13 degree 20 minutes. There are 27 of these units in a month. The sum of the longitudes of the sun and the moon is divided into equal divisions called yogas. We consider the sidereal longitudes, we call it as Nirayana longitudes in Sanskrit. The sum of the sidereal longitudes of the sun and the moon is converted into minutes and then divided by 800 minutes. The quotient represents the number of yogas completed, and hence the current running yoga is obtained by adding 1 to the completed number of yogas, similar to what we have done in the case of tithis and nakshatras. Yoga here, we need to note this, is a function of the declinations of the sun and the moon. In fact, it is used in determining when the two bodies have the same declinations numerically. This is called parallel aspects in Western astrology. In the earliest astronomical work, Vedanga Jyotisha, only Vedanga Jyotisha is the earliest astronomical text available. Only 2 yogas are mentioned which correspond to parallel aspects, and later, in a later stage, mathematical astronomy, they have recognized 27 yogas. So the list of yogas are given for your information. So they are named as Vishkamba, Preeti, Ayushman, etc. And the last one is Vaidhrita. All these names are in Sanskrit. And one example has been worked out here for the same date by considering the longitudes, sidereal longitudes of the sun and moon. We take their sum and divide it by 800 minutes, converting the longitudes also into minutes. And for in this example, so we got the quotient as 9.34, and it means that 9 yogas are completed for the given date at the time, and the 10th yoga is running. And from the table, the 10th yoga, name of the 10th yoga is Ganda. It is called as Ganda Yoga. Now, let us come to the fourth part of the Panchanga, which is called as Karana. Here, the Karana is nothing but half of the true Tithi. That means half of the lunar day or lunar phase within which it falls. There are 4 fixed Karanas as in the lunar month, which occur in the last Tithi of 1 month and the first of the next. After the first Tithi comes a sequence of 8 repetitions of 7 movable Karanas. We have 2 different types of Karanas. Totally, we have 11 Karanas identified, and 4 of them are considered as immovable, and they are called as Sthira Karanas in Sanskrit, and 7 are considered as movable, and they are called as Chara Karanas in Sanskrit. The names are given here. I'll just read 2 or 3 names for your information. The movable Karanas are named as Bhava, Balava, Kaulava, Taitila, Gara, Vanich, Visti, and immovable, which are Sthira Karanas, are named as Shakuni, Chatushpada, Naga, and Kimstugna. In each Tithi, the first half is 1 Karana and the second half is the next Karana, so that each Karana is situated at 6 degrees of angular distance between the sun and the moon. In the particular 4 half tithis, namely the second half of Krishna Paksha, that is the darker fortnight, Chaturdashi, that is the 14th tithi, the 2 halves Amavasya, and the first half of the Pratipat, that is the first day, or the Sthira Karanas, that means immovable Karanas. These 4 names will be on those tithis respectively. Then from the second half of the Pratipat, that is the first day of the brighter fortnight, we have the Charana Karanas, namely Bhava, Balava, etc., repeating the cycle of 7 Karanas each time, 8 times for 30 tithis. Next, the last and the 5th part of the Panchanga I'll take up. That is Vara. Anyway, before going to Vara, I just want to show that we have calculated the Tithi, Nakshatra, Yoga and Karana, these 4 parts of Panchanga for the day and for another date. And for that days, when we consider the moon's position as 176 degrees, 27 minutes, 33 seconds, and sun as 309 degrees, 56 minutes and 57 seconds. So using the mathematical formula explained, so we got the Tithi for that day is 19. 19 has exceeded 15. That means it shows that the running Paksha is Krishna Paksha, that is the dark fortnight. And it is the 4th day of the dark fortnight. The Tithi is called as Chaturthi, and that is the 4th day of the dark fortnight. And for the same day, Nakshatra number is 14 and the running Nakshatra is Chitra. It is called Spaika. And the yoga for the same day, the number is 10. Therefore, the name of the yoga is Ganda. And the Karana for the running Tithi is, the number is 2. Therefore, the Karana name is Balava. Now let us come to the last part or the 5th part of the Panchanga, which is the Vara, that is the weekday. Finding the weekday does not require any planetary positions for that matter. A 7-day week is followed in India. The weekdays are named as Ravivara, Somavara, Mangalavara, Budhavara, Guruvara, Shukravara and Shanivara. Vara means weekday. The Ravi, Soma, Mangala, etc. They are the names given for the weekday. And these names correspond to Sunday, Monday, Tuesday, Wednesday, Thursday, Friday and Saturday respectively. The 7 days of the week are named after the 7 luminaries: the Sun, the Moon, Mars, Mercury, Jupiter, Venus and Saturn. Historically, it is important to note that the mention of 7 weekdays of the week is not there in Vedas or the earliest astronomical text called Vedanga Jyotisha, and not even in the Indian epic Mahabharata. And the weekday is supposed to be of Egyptian origin. Now let us come to the schools of parameters, which are called as Pakshas in Sanskrit. The general similarities of model and method did not prevent classical astronomy works from significantly diverging in some aspects of their content. In particular, different choices about their fundamental parameters, mostly in the values of celestial bodies, revolution numbers, and consequent mean velocities, streamed such works into one of the following few categories, generally called as Pakshas or schools of astronomy. The first school of astronomy is named as Brahma Paksha. The astronomy of Brahma is mentioned as a source at the close of the Aryabhatiya of Aryabhata. The Aryabhata is the pioneer astronomer of India. He composed Aryabhata 1, Aryabhatiya, about 500 CE. The seminal surviving exponent of this system, in which the time begins at sunrise at the start of the Kalpa, that is beginning of a Kalpa, is the Brahmasputa Siddhanta of the great astronomer Brahmagupta, composed in 1628 CE. the canonical Siddhanta Shiromani of Bhaskara II in the 12th century also follows this. So its main region of influence appears to have been northern and western areas of India, although the Siddhanta Shiromani was famed throughout the subcontinent. Siddhanta Shiromani is the magnum opus of Bhaskara II. Now with the second Paksha, here is the Arya Paksha, Aryabhata I, followed the Aryabhatiyam of Aryabhata I. The author of the Aryabhatiya developed in its own set of parameters like the Brahma Paksha using a sunrise epoch, but with a different division of the Mahayuga. This became the dominant Paksha in southern India. An ardent follower of Aryabhata was Bhaskara I in 629 CE, who explained elaborately Aryabhata's system. Saura Paksha is another school of astronomy, which is the midnight epoch system, and it is the sun school embodied in a recession of the Surya Siddhanta dating to around the 8th century. It gave rise to many works, especially in central and eastern India, and like Brahma Paksha, seem to have been the basis of many tables texts. And in this future slides, I am going to take up a prominent astronomical table called Makaranda Sarni, which is based on Saura Paksha, which is based on a text called Surya Siddhanta belonging to Surya Paksha. Next, another important school of astronomy is Ganesha Paksha, and this is based on the Grahalagavam of Ganesha Daivagna. This parameter system was set out in the handbook called Grahalagava, which was composed by the Maharashtrian astronomer Ganesha in 1520 CE and was widely adopted in northern and central India. It is a modified combination of parameters from other pakshas or other schools of astronomy based on Ganesha's own observational tests of their accuracy. Here I would like to mention the astronomer and mathematician Ganesha Daivagna has produced very highly innovative works. He has composed the whole text called Grahalagava, dispensing with the trigonometric functions sine and cosine, and he has done it successfully by giving proper and approximation for the trigonometric functions depending on the circumstances, and he has composed the entire text for the for the benefit of the Panchanga makers and who are not good mathematicians, but still they are able to make use of his handbook and compute Panchanga and do the calculations. So that is the highlight of his work. And the Panchangas or the Indian almanacs are based on traditional treatises. They are called as Siddhantas, so which we have discussed. These Siddhantas, they are the basis for the schools of astronomy. We have Surya Siddhanta, Brahma Siddhanta, etc. Since the direct application of these texts are cumbersome and tedious, and for the day-to-day positions of heavenly bodies, the Panchangas compiled annually based on the Sarinis, I mean astronomical tables, which are based on these Siddhantas. And they belong to different schools of astronomy, as mentioned above, before. The popularly used Indian astronomical tables belong to different schools, and these different schools conform to the parameters and procedures respectively of Surya Siddhanta, which is a basis for the Saura Paksha. Aryabhatim is the basis for the Arya Paksha, and Brahmasputa Siddhanta is basis for the Brahma Paksha, and the Grahalagava of Ganesha Daivagna for Ganesha Paksha. In addition to this, we have Navina Druk Siddhanta also. This is also used now. Now let us come to the astronomical tables. I would like to name few astronomical tables belonging to different schools of astronomy. The prominent one is the Makaranda Sarni, which is composed by the astronomer Makaranda in 1478 CE, Ganakananda of Suryacharya, who is the son of Baladitya, in 4047, March 16, and the Rama Vinoda by Ramachandra in 1519 CE. We have another many more sets. Ravi Siddhanta Manjari by Mathuranath Shukla in 1609. Pratibhagi and Tragerti manuscripts. These are all based on Surya Siddhanta. Ganakananda of Surya is a Karna text, popular mainly in Andhra Pradesh and Karnataka, the districts of India. Pratibhagi and Tragerti manuscripts are the tables used by the Shukla Paksha followers of the Karnataka state in India. The important tables belong to Brahma Paksha or Brahma Tulya Sarini. The epoch of this is 1183 CE. Mahadevi written by Mahadeva in 1316 CE. Jagat Bhushana written by Haridatta in 1638 CE. And Kechara Deepika by Kalyana in 1649 CE. Tithi Chintamani and Grahalagava Sarini. The epoch of this is March 18, 1520 CE. Are the tables based on Grahalagava of Ganesha Devagna, which has been mentioned already. Similarly, there are tables belonging to other schools also. In fact, Vakya tables are very interesting. They are used mainly in Kerala and Tamil Nadu states of India. These tables are composed by a legendary person called Vararuchi, and these Vakya tables comprise Sanskrit sentences which are numerical chronograms based on the Katapayadi system. Unlike the other Indian astronomical tables, the Vakya system comprises simple Sanskrit sentences in which each letter represents a number following the Katapayadi number system. The number represented by these sentences are called as Vakyas in Sanskrit. Vakya means sentences. These sentences give directly the true positions of the heavenly bodies. The Vakya system is based on Arya Paksha. That means it is based on Aryabhatiyam of Aryabhata 1. And we have another classification system of Indian astronomical tables. They are categorized into 3 different types based on their arrangements. They are categorized as mean linear, true linear, and cyclic. In mean linear arrangement, mean motion tables are accompanied by the tables of equations, Grahalagava Sarini and Ravi Siddhanta Manjari, Makaranda Sarni, and Brahma Tulya Sarini. These are the 4 examples which belong to mean linear type tables. In true linear mean motion, tables are accompanied by the true longitude tables, whereas in the cyclic arrangement, true longitudes are given for several years of the goal year periods. Examples are Mahadevi, Rama Vinoda, and Kechara Deepika. They are true linear tables. Jagat Bhushana by Haridatta is a cyclic table. Now let us have some information about a particular table, Makaranda Sarni, which belongs to the School of Astronomy of Saura. And we have some special features of this text. This is the most popular text in among the Indian astronomical tables. These tables are the tables with explanatory shlokas. The verses are composed by the Makaranda, son of Ananda at Kashi in 1478 CE. Kashi is the place. This Sarini belongs to Saura Paksha. In fact, MKS, here afterwards I'll call this Makaranda Sarni as MKS. MKS is the most popular among the Sarinis of the Saura Paksha, and most almanac makers in India adopt this system, this table, for computing the Panchanga elements like Tithi, Nakshatra, etc., and also for computation of planetary positions and eclipses. See, the tables that are given in the Makaranda Sarini are the ending moments of the Panchanga elements like Tithi, Nakshatra, Yoga, Karana, etc. The mean longitudes. There are tables given for finding the mean longitudes of the Sun, Moon, and 5 star planets, Mars, Mercury, Venus and Saturn. Jupiter, Venus and Saturn. The equation of center, it is called as Mandaphala, which is a correction to be applied for finding the true positions from the mean position. And we have the tables for equation of center of each heavenly body in Makaranda Sarni, and also another correction equation to be applied for finding the true positions of the star planets, which is nothing but the equation of conjunction called as the second equation by Ptolemy. So the tables for this is also given. The moments of solar ingress, they are called as Sankramana or Sankranti in Sanskrit. The solar ingress into zodiacal signs and also to the 27 asterisms are given. The sun's declination, table for finding sun's declination, which is called as Kranti in Sanskrit, and latitude of the moon called as Shara or Vikshepa in Sanskrit. Angular diameters of the sun, moon and earth shadow, they are called as bimbas. For computing lunar and solar eclipses, and also the method of computation of lunar and solar eclipses, making use of these tables are all explained in Makaranda Sarni. There are many works and commentaries on this Makaranda Sarni. This shows that this is how why this is so famous and popular among the Panchanga makers. So many have written their commentaries on Makaranda Sarni. The famous commentator Vishwanatha Daivagna, he is the major commentator of this Makaranda Sarni. He has composed a useful commentary on this with a large number of examples to elucidate the procedure of this in 1540 CE. And we have the rationale for these tables composed by Gokulnath Daivagna, and the explanatory commentary by Divakara, and also we have Hindi translation of these tables by Acharya Ramajanma Mishra and Gangadhara Tandon. So many such works are available in Sanskrit and Hindi language. Now, the special feature of Makaranda Sarni, if you come to this point, the author has incorporated many changes to yield better results during his time. He has given Ahargana Valli table. This is required for finding the Ahargana. I will explain what is Ahargana in the next slide. For the given date, which is the heap of the day, which is a required parameter for finding the mean positions of the planets. So he has expressed Ahargana in sexagesimal system. The units that he has used to represent them as Rashi, Amsha, Kala and Vikalas. These are the Sanskrit names for signs, degree, minutes and seconds, in which the Adhika Masa, which is nothing but the intercalary month, concept of a lunar calendar is also incorporated, so that finding the Ahargana from this table is easier when it is compared to the procedure of finding Ahargana from the other astronomical texts, which includes the incorporation of the Adhika Masa, etc. separately, to be included separately. The another highlight of the text is that the author has reduced the 4 stages of correction for star planets to obtain the true position from the mean position to 3 steps by combining the equation of center correction. So I will, that means in Indian system, they apply the equation of center and equation of conjunction for obtaining the true positions of planets from the mean position in 4 stages. The 4 stages of application is combined to 3, and his combination, combining the 4 stages to 3 stages has not affected the accuracy of the result, and he has done it in a technically good manner. In the computation of lunar and solar eclipses, the angular diameters of the sun and the moon and the earth's shadow are obtained from moon's duration, moon's Nakshatra mana, that means duration of an asterism or lunar mansion, and the sun's ingress. So these are the 3 special highlights of the text. Just a minute.
aprovecho para invitarlos a hacer alguna pregunta si quieren que le hagamos al final a la doctora. Gracias.
Hello, sir. Hello, sir.
Hi, doctor. I was just asking the audience to make any questions that they want after you finish your lecture.
Yes. So this is the cover page of the astronomical table Makaranda Sarni. It is written here in the Sanskrit as Atha Makaranda Sarni Udaharanas Saha Prarambha. That means it is the beginning of the examples from the Makaranda Sarni. This is the cover page of the Vishwanatha Devagna's commentary. And here are the tables. They look like this. It is a folio taken from the Makaranda Sarni table. So these are the arrangements here, the rows and columns. Now, when I spoke about Ahargana means in Sanskrit heap of days. The calculation of this, it is the number of days elapsed since a chosen epoch. Literally, it means heap of days. The calculation of Ahargana depends on the calendar system that is followed. Intercalary months play an important role in the calculation of Ahargana. See, as I mentioned already, for the purpose of finding the mean positions of planets for any given day, the number of civil days elapsed since the beginning of a chosen epoch must be determined first. Then the duration of time in days multiplied by mean daily motion of a planet gives the mean angular distance covered by the planet during that period. From this motion, the completed number of revolutions, that is multiples of 360 degrees, are removed, and the remainder, when added to the mean position of the planet at the epoch, gives the mean position for the required day. So that is why the Ahargana is the very basic, important parameter for finding the mean positions of the planets. Literally, Ahargana means heap of days, and according to Siddhantas, it is the number of mean civil days elapsed at the midnight or mean sunrise from the Ujjaini meridian. This meridian passes through Lanka, supposedly on the equator. The calculations of Ahargana depends on the calendar system followed. The traditional Hindu calendar follows both the lunisolar and solar system, and the former is pegged on to the latter through the intercalary months. So in Makaranda Sarni, the Ahargana is expressed in sexagesimal system, and as I said already, they are expressed in terms of signs, degrees, minutes, and seconds, and this will enable us to convert this MKS Ahargana into Kali days, and in turn we can find out exactly the modern date for the given Shalivahana Shaka date of the year. So these are the tables of Ahargana given in Makaranda Sarni, and they are actually converted into Indo-Arabic numbers. They look like this. So they have given for the years with a difference of 16 years. So they start from 1628, then after adding 16 years, 1685, like that, they go on giving. We can also extend this table for our requirement. And the remaining 16 days, we have another table, 1 to 16. And also for every fortnight, the corresponding components are given. So now we are supposed to use these three tables for computation of Ahargana, and an example is shown. Maybe I have a shortfall of time. So this is how Ahargana is computed using the table is mentioned, shown here for the given Shalivahana Shaka year. And an example is computed here. I have taken the date corresponding to 2017. So Ahargana is calculated according to MKS, and also we have taken the Kali Ahargana from the modern tables. So they are coinciding exactly. So this is the table of the equation of center for star planets. It looks like this, a folio from the table, which is given for the equation of conjunction of the Mars, Shigrapala table for Mars. So these are all the tables for different planets, and they are written in Hindu Arabic numbers. They look like this. Now, see, we have calculated, because I am not going to show the mathematical calculations of all these mean position, true positions according to the table, because it will be too mathematical for to listen. And see, I just want to show this comparative table. So we have taken the mean positions of the heavenly bodies, 5-star planets, for the date 1620 May 15 for Ujjaini meridian, and this corresponds to Shalivahana Shaka of 1534, which falls on the month of Vaishaka, Shukla 15. That means it is the full moon day of that lunar month. So we have taken the mean positions of the planets according to 3 different texts. One is the Makaranda Sarni table. The other one is the Surya Siddhanta, written here as SS, Surya Siddhanta, on which the Makaranda Sarni tables are based. And then we have compared the values with the modern. So we will observe here the values of the mean positions of the star planets according to Makaranda Sarni and according to Surya Siddhanta. They are equal. If they differ in the seconds, fraction of seconds in time unit, in the units, degree, minutes, seconds. Here actually they have put here as 9 hour, 27 degree, 21 minutes, 38 seconds, etc. This R stands for sign. So 9 hour means 9 signs. And here, when we have compared this with the modern, we can see that the difference between the values are less than half a degree. So we have this position of the Mars as 9 signs, 29 degrees, 21 minutes, 38 seconds, and modern values for the same date is 9 sign, 21 degree, 9 minutes and 26 seconds. So the difference will be even less than a degree. So like that, we can compare the values for the other planets also, and the true positions of the planets are also compared. They are also well coincide with the values obtained from MKS and Surya Siddhanta. The difference is less than a degree for even true positions of the planets. So that means the tables were computed very accurately, adopting the interpolation techniques. So that is why when the Panchanga makers, even if he is ignorant of certain mathematical concepts also, he can make use of the table for compilation of the annual almanac called Panchanga. So this is the table for computing the angular diameter of the sun and moon. Particularly, we require this for computation of eclipses. And the speciality of the text is he has given, normally other Siddhantic text gives the diameter of the sun moon in terms of their motions. Here it is expressed in terms of the duration of a lunar mansion and also solar ingress into 12 different zodiac signs. So that is the special highlight, and the same table is put in Indo-Arabic numbers. So it gives here the sun's ingress to different rashis corresponding values, and also means the duration of a nakshatra for different position of moon. Now, when we take up the, say, so far we have taken a text called Makaranda Sarni, which belongs to the Saura school of astronomy. I have taken another text called, another astronomical table called Tithi Chintamani, which belongs to Ganesha Paksha, based on the Grahalagam of Ganesha Daivagna. Importance of the text is this. These tables are based on Grahalagam and composed by Ganesha Daivagna in 1525 CE. This is a popular text and widely used even to this day for computation of almanac followers of Ganesha Paksha, by the followers of Ganesha Paksha. And it consists of the astronomical tables to determine Panchanga elements, or the almanac components called Tithi, Nakshatra, Yoga, Karna, etc. And also there are tables for finding the solar ingress into 12 zodiac signs and 27 asterisms. So there are two different the versions of this table. The one is called as Lagu Tithi Chintamani and the other one is called Brihat Tithi Chintamani. Lagu Tithi Chintamani has got some 18 shlokas with tables. Brihat Tithi Chintamani comprises of 27 verses, and in the text, these verses and tables, verses will explain how to make use of the table for finding the Tithi Nakshatra Yoga Karna and also computing solar ingress. So the details are given here. I will show you a folio of Tithi Chintamani. It is given like this. The numbers heading the rows and columns are 0, 1, 2, etc. And for each number, we have the corresponding components of Tithi, Nakshatra, Yoga, and Karana. So making use of this, almanac maker can compute these 5 parts for each day. These are the folios from Tithi Chintamani. The 18 shlokas of this text, as I said, they explain how to make use of the tables to computation of the Panchanga elements, and the brief summary of these shlokas like this. Shloka 1 explains the, it is an invocatory verse, and Shloka 2 gives finding the Lord of the Year, which is a required basic parameter for further computation. Shloka 3 is longitude difference correction. Then we have the table for epoch and the synodic time offsets, anomalistic time offsets, corrections to anomalistic time offsets and weekday time offsets, modified weekday time, then use of correction tables again for Tithi Nakshatra Yoga are explained from Shloka 11, 12, 13. I mean verses 11, 12, 13. And excess and deficiency of a day, they are called as Kshaya and Buddhi in Sanskrit. Determining lunar mansion and yoga, that is Nakshatra Yoga. Solar ingress to zodiac signs and asterisms, and intercalary and omitted months, which are called as Adhikamasa and Kshayamasa in Sanskrit, and also comparison of the parameters with the different texts. That is also very good thing about this table. Ganesha himself shows what are the parameters used in this table and what is the difference between the parameters that he has used and how it differs from the other text. So these are the highlights of the text, and I would like to acknowledge the Indian National Science Academy, New Delhi, for sponsoring the projects to work on the 2 important tables called Makaranda Sarni and Tithi Chintamani. These are the references for the benefit of the scholars who are interested in Indian astronomy. Thank you very much, sir.
Thank you very much. It's been a wonderful lecture, full of data and full of interesting things. And we have here some questions for you, Doctor. Okay. The first question that I have is, do we understand well Indian Panchanga means an astronomical calendar?
Yes, it is an astronomical calendar.
And how long it covers? It covers a year?
It is for a year, 1 year.
1 year, okay.
Every year it will be computed.
So this calendar, this Panchanga is updated once a year. Every year we have a new one.
Yes, every year we will have a new one.
Okay, thank you. Where can we find this publication in case we want to have access to one Indian astronomical calendars?
We have one Rashtriya Panchanga published by the Government of India.
Okay.
And also we have many private almanac makers, and so there are many religious organizations which bring out these almanacs yearly.
Okay.
But scholars who can compute the Panchangas.
Understood. Thank you very much. And there is another question here. Are the tithis lunar phases?
Yes, yes.
Mhm.
Yes,
So
they are
we
lunar phases.
lunar phases. So we usually have 8 lunar phases here in the western part. So you
Yes, yes.
you use 30 lunar phases.
30. The prominently there are 8 phases recognized, but considering the longitudes of the sun and moon, they have divided into 30 equal parts. No, not
Wow.
equal. Sorry, it is not equal. The duration of a tithi is not equal. They have divided into 30 parts, which depend on the duration of each part depends on the position, the motion of the sun and the moon.
Wow. It's very, very interesting. This this way of treating the lunar phases is very interesting for us. You named also that we have you have 27 yogas, and you named the different names of the yogas.
Yes, yes.
What does these names mean in general? Are they associated to what? The names of the yogas?
Not very much. They are all Sanskrit names given.
Okay. We have another question here. What other calendars do you use? What other calendars do you use in your astronomical calculations?
Yes, lunisolar and solar calendars we use.
Lunisolar, okay.
Yes.
We also noticed that the name of Jupiter is Guru.
Yes, name of Jupiter is Guru.
Guru. What does it mean, Guru?
Guru literally means big one.
Oh, all right. The big one.
Yes.
Oh, wonderful. That is wonderful. Okay, here are a couple of questions additional. Yes, are these tables updated each year? You said that yes, they are updated. And finally, the sum of the Nirajana longitudes of the sun and the moon is divided in 27 equal divisions. Are these the yogas, right?
Sidereal longitudes. Nirayana means sidereal.
The longitudes, sidereal longitudes.
Yes, yes, yes.
Why do you use 13 degrees and 20 minutes?
Yeah, that's what I said. The moon takes 27.32 days to go around the earth once. So approximately one asterism is equal to 1 day in lunar terms. So that's why it is divided into 27 lunar mansions or asterisms.
Very well, thank you very much. And the last question here is the Panchangas are based, you mentioned that the Panchangas are based on traditional treatises like Surya Siddhanta, but Brahma. Can you tell us a little more about these traditional treatises?
Yeah, we have the major astronomical text. They are called as Siddhanta texts. Surya Siddhanta is one example. Aryabhatiyam is also a Siddhantic text written by Aryabhata I. And we have Brahmasputa Siddhanta by the astronomer Brahmagupta. And the Siddhanta Shiromani from Bhaskara II. These are all called, they are bigger texts of astronomy. They explain the procedure for computing the planetary positions and eclipses and other phenomenon. And with the explanation, mathematical procedures are also given, and the corresponding theory behind that is also explained. These are the Siddhantic texts. But the thing is, as I have mentioned, there are different stages of obtaining the true positions of a heavenly body from the mean position. Computation of mean position itself is a bigger task from the chosen epoch, making use of these texts, and then we have to apply many corrections for getting their true positions. And for applying each equation of center, equation of conjunction, there are different stages. So they do it in different stages, and also they make use of actually repeated application of these for more accuracy of the results. So for one day, computing the Panchanga elements like Tithi, Nakshatra, etc., we require minimum the positions of the sun and moon, and for computing the true position of moon requires more number of equations. So we have to apply the equation of conjunctions and many other correction factors for obtaining the position of the moon. And after finding these two for a given day, again finding these 5 elements will be difficult. So the tables have simplified the mathematical procedure by giving the correction factors in the form of the rows and columns, so that with a particular constant, when they find out for the given year, so they can go on by taking the corresponding correction values from the table, simply adding, multiplying, or making use of the interpolation technique. They will find out the correction factor for that particular day, and computation will be more easier because they can go on adding some constant factor, so that for subsequent days they can get it easily. Because they will have to compute, they compile the Panchanga for 1 year, means 365 days. So calculating the positions of the heavenly bodies for each day using the Siddhantic text will be a cumbersome job. So that's why the computation process is made easier by these astronomical tables.
Wow, it's been a very interesting and wonderful talk, a wonderful lecture. Thank you, Dr. Uma. Thank you for your time. And we appreciate very much your time and your information, sharing with us all this useful information in tables that are from many years, originated many years ago. And we appreciate your time. Thank you, Dr. Uma.
Thank you very much, sir. Thank you very much for inviting me, and thank you for your cooperation.
And we look forward for more in the future, and to know more about Indian astronomy. Thank you, Dr. Balachandra Rao.
Thank you so much, sir. I convey this also. He is my guru in this field. He is my teacher in this field, and he is my guide.
Give it our regards to him, please. Thank you. Have a nice day and a nice Sunday. Thank you very much.
Thank you so much, sir. Thank you very much. So I have taken more of your time, so kindly pardon me for that.
Thank you.
Thank you.
Bye bye.
Okay. Leave off this session?
Yes. I'm going to close the session, the meeting now. It's okay?
Okay. Thank you so much. Thank you once again.
Thank you.